Okay, I'm going to go over a few problems here. That way you guys have a general understanding as far as how to solve some of these specific problems. The first one here is going to be when will 5 millicuries of iodine 131, given the half-lives given there, and 2 millicuries of phosphorus 32 with the half-life given there, are going to have equal activities. So how do we go about finding that? Well, since the answer is when these two will be equal, obviously time is going to be the same for both types of problems. So the initial activity here of iodine 131 is 5 millicuries. For the phosphorus 32, it's 2 millicuries. And you can see the iodide initial activity and the phosphorus initial activity. You see the half-lives. We're going to symbolize the activity at this time t when they're equal to be represented with this. And then for phosphorus, it'll be this. In the equation for solving activity, given the initial activity, of course, it's going to be this particular equation. So A is equal to A naught E to the raised to the minus lambda times T. So what are the decay constants here? Lambda is, of course, 0.693 divided by the half-life. We know what that is. So we've got our decay constant here. Same thing for phosphorus. We know what that is. So here's the algebra. And I know this looks a little messy, but this is how we're going to get to the equation that we need. So we've got the initial activity of the iodide here, or this is the activity when they are equal to each other. And this is equal to the initial times the decay constant and all that stuff. Same thing holds true for the phosphorus. We're just putting it on this side of the equation. We know these two are equal, so we're taking this part of the equation out, and we're coming to here. Here, we're going to divide both sides by the initial activity of the iodide. We do, it cancels over here, and we're left with it over here. So this leaves us with e to the minus lambda 1t is equal to all of this stuff over here. What we're going to do is since all of these terms over here are being multiplied by each other, we're going to strip this and this off into one term, and we're going to put it right there. And then we've got this part over here that remains, this remaining part right here. Now, what we're going to do is we're going to change this from a negative exponent to a positive. In order to be able to do that, we take this and put it in the denominator, and so that's why it looks like the way it does. So the next step is we're going to multiply both sides by this term. What happens is that this disappears out of the denominator and is eliminated by what's in the numerator. So it ends up over here, basically. So all of this stuff over here disappears. So we've got this times this is equal to this ratio. So now, how do we simplify all of this? Well, as we're going through, we've got e raised to this and then e raised to this. By the properties of logarithms, all we have to do is to take this exponent and add it to that exponent, and this is what we come up with. So we get e raised to the minus lambda 1 times t plus lambda p, lambda I, I'm sorry, I don't know why I keep calling that one, lambda p times t. In order to get rid of the e, in other words, in order to be able to access the stuff that's up here in the exponent, we apply a logarithm to each side. When we do that, particularly for something that has a base of e, this exponent actually just falls down and becomes a coefficient of the natural log of e. And so if I were to write that, it would look something like this. It would be natural log of e raised to the minus lambda I, and sorry for that looks, okay. Let's try this, just try to do this a little better. E minus T, and draw another set of parentheses around there, plus lambda P times T. What that basically ends up meaning is that you end up with minus lambda I T plus lambda of phosphorus times T times a natural log of E. That is just 1. And so what you're left with here is this. Since we took the natural log here of both sides, then this becomes the argument of the natural log application over here. Factored out a T here. And now that we have all of this assembled and whatnot, we can take a step here of multiplying both sides by the coefficient of the T here. When we do that, we have to do it to both sides. That means it disappears over here. And that means we're left with time, which is what we're looking for, because the question was, when will these two have equal activities? So we were looking for the time, and it's times all of this garbage over here. We know these two values. We had them up at the top. This one was 2 millicuries. This one was 5. We know what the decay constants are for each one of these. And then we crank through the mathematics here, basically the natural log of 2/5, which is this. Adding these two together, we come up with minus 0.038, and with days to the -1. When we go through and we do the math here, we end up with 24 days. So that's where that comes from. So in 24 days, this amount of iodide 131 and this amount of phosphorus 32 are going to have equal activities. So that's where that one comes from. Next. Okay. A patient is treated on a Monday with a radioactive iridium-192 source using the high dose rate remote afterloader treatment unit. The treatment duration to deliver a given dose is 289 seconds. The patient is to be treated again on Wednesday at the same time of day. The dose to be delivered is the same as on Monday. The activity of the iridium will be lower on Wednesday, therefore the treatment time must be increased. What should the treatment duration be for the Wednesday treatment? So the half-life is 74 days. So we're going to solve for the treatment time on Wednesday. So we know the difference in days between the two treatments. We know what the half-life is. We know the treatment time on Monday is 289 seconds, and we know the Monday activity. We're going to just reference that as 100% or just 1, just in order to be able to have some level of activity to reference, some absolute value. The calculated values, the decay constant of iridium-192 turns out to be, using the formula here, lambda is equal to 0.693 divided by 1/2. So we end up with 0.00936. So the Wednesday activity, since we're going to call this 1, we know what the decay constant is because we just tabulated it up there. And we know what the difference in the day is going to be because we're doing this from Monday to Wednesday. We're going to call this A sub naught, essentially, and this is just going to be regular A. So we know what the difference is. So we put all this information in, calculate this, so we got 0.981. So We know that the treatment time on Wednesday times the activity on Wednesday should be the same as the treatment time on Monday times the activity on Monday. We solved that equation for the treatment time on Wednesday. We know what this is. We know what that is, and we know what this is. This is 0.981, which we just found out. This was given to us. By doing that, we come up with 295 seconds. This is greater than the 289 that we started out with. So now we're going to move on to problem number 3. Sorry, I looked over problem 3 and it looks like it was a repeat of the others. So those are the only 2 problems in this section. I'll work some more a little bit later.